Hello! Good day everyone! Again, this is Gabriel Gamana, and as I mentioned in the previous video, this series will tackle 7 different chapters, from nonlinear equation in one variable to partial differential equations. So to start the series, this video will focus on chapter 1, discussing the first topic, which is the bisection method. But before I dive into the topic, let me first discuss the bracketing methods. So let's start. Bracketing methods are techniques that requires two initial guesses. These initial values must contain the roots for the solution to converge. Say for example, the equation x squared plus 8x plus 15 equals 0 has the roots of x equals negative 3 and x equals negative 5. If we are going to solve the value of one of the roots, we have to enclose them by our initial guesses. Say if we choose to determine the first root x equals negative 3, our initial guesses can be negative 4 and negative 2. Or, if we wish to determine the second root, which is x equals negative 5, our initial guesses can be negative 6 and negative 4. In that way, the solution under bracketing methods will converge only if we choose proper limits or initial guesses. Say for example that we choose to determine the first root, which is x equals negative 3, but we select our initial guesses as negative 2 and 1. Since the equation does not have any roots between the chosen limits, the solution will not converge. See to it that the chosen limits possibly contains the roots. Take note that bracketing method always converge only if our initial guesses are correct. So that's it for the bracketing method. We will now dive into the first topic, which is the bisection method. The bisection method, which is alternatively called the binary chopping, internal halving, or Bolzano's method, is one of the incremental search method in which the interval is always divided in half. In other words, we will take the average of the upper and lower limits. Here is the procedure of bisection method based from the textbook reference. I know it's a bit wordy, so let me explain it with a graphical presentation. Say that we have a graph of polynomial equation, and we are asked to determine the roots. According to the bisection method procedure number 1, we have to choose lower and upper limits. That's when we substitute it to the function, the sign changes over the intervals. This instruction only assures that our initial guesses will contain the roots. Say for example that we choose our lower limit to be x equals 3 and our upper limit to be x equals 6. When we substitute this value of x to the polynomial equation, we will notice that the upper limit has a positive value and the lower limit has a negative value. And that satisfies the procedure number 1, that the multiples of the function is a negative number. It only means that our bracket or limits has contained one or more roots. Say for example that we choose a different limit, like x equals 4.5 and 6. Obviously, the bracket or limit does not contain any roots, and we can verify this fact without providing a graphical presentation, but by simply evaluating the value of the function using the set limits. We can determine if the initial guesses contains the root. If we satisfy procedure number 1, we can now proceed to procedure number 2, which is taking the average of the upper and lower limits. Then immediately proceed to procedure number 3. On this procedure, we will decide if who between the upper and lower limits will replace by the defined value of x, or should we stop the solution since we reach the convergence. Our decision will still base on the idea that the multiples of the function should be a negative in sign. With this bracket, the upper limit must be replaced since the lower limit satisfies procedure number 3. And by repeating procedure 2 and 3, we have to replace the lower limit since it doesn't satisfy procedure number 3. By repeating the process, we are now decreasing the size of the bracket until the bracket's width will become negligible. And that's where we say that the solution has converged. Well, throughout this course, convergence will be defined by the relative error, given by the formula epsilon sub n equals the absolute value of the present value of x minus the previous value of x all over the present value of x, and it should be less than the value of the stopping criterion. It means that we will compare the defined value of x from the previous iteration, and if the difference is too small, we will stop the solution and conclude that the convergence has reached. For better understanding, let's solve a problem using bisection method. Find the roots of the equation where f of x equals 0 with the stopping criterion of 0.001, where f of x is a function equals to 3x plus sine x minus e raised to x. To start the solution, let's set this area as the number of iteration. Lower limit, upper limit, and the refined value. For our first iteration, let's assume that our lower limit is equals to 2 and our upper limit is equals to 4. But before we proceed to the defined value, let us first implement the procedure number 1 of bisection method to make sure that we capture the roots within the initial guesses. By substituting the lower limit to the function, f of 2 is equals to 3 multiplied by 2 plus sine of 2 minus e raised to 2 is equals to negative 0.480. And by substituting the upper limit to the function, f of 4 is equals to 3 multiplied by 4 plus sine of 4 minus e raised to 4, and that is equals to negative 43.355. Since both values have the same sign, the solution will not converge and we have to update our initial guesses. Say our new limits are negative 0.5 and 1.0. Again, by implementing procedure 1, we have f of negative 0.5 is equals to 3 multiplied by negative 0.5 plus sine of negative 5 minus e raised to negative 0.5, and that is equals to negative 2.586. And for the upper limit, f of 1 is equals to 3 multiplied by 1 plus sine of 1 minus e raised to 1 and equals to 1.123. Since the value satisfies procedure 1 by having different signs, we will now proceed to procedure 2 by taking the average of the limits. Negative 0.5 plus 1 all over 2, and that will give us 0.25. Then, we will substitute this value to the function in preparation for procedure number 3. So, f of 0.25 is equals to 3 multiplied by 0.25 plus sine of 25 or 0.25 minus e raised to 0.25, and that is equals to negative 0.287. Since the resulting value is negative, we have to replace the limit that has the same sign when plugged in to the function. That means for iteration number 2, instead of 0.5, the lower limit will become 0.25 and the upper limit will retain as 1.0. We will immediately implement procedure number 2 by taking the average of the defined limits to determine the defined value of the roots, and that will give us 0.625. Then again, we will substitute this value to the function in preparation for procedure number 3. So, f of 0.625 is equals to 3 multiplied by 0.625 plus sine of 0.625 minus e raised to 0.625, and that will give us 0.592. Since the resulting value is positive, we have to replace the limit that has the same sign when plugged in to the function. But before that, let's check the relative error of the defined roots. If we already satisfy the stopping criterion, we don't have to proceed the solution anymore. So epsilon sub n is a function of the absolute value of the present x minus the previous x all over the present x, and that is the absolute value of 0.625 minus the previous, which is 0.25, all over the present, which is 0.625, and that is equals to 0.6. Still far away from 0.001. That means more iteration to come. For iteration number 3, the lower limit will remain 0.25, while instead of 1.0, the upper limit will become 0.625. Again, implementing procedure number 2 by taking the average of the defined limits to determine the defined value of the roots, and that is 0.25 plus 0.625 all over 2 equals to 0.438. Then again, we will substitute this value to the function in preparation for procedure number 3. So, f of 0.438 is equals to 3 multiplied by 0.438 plus sine of 0.438 minus e raised to 0.438, and that is equals to positive 0.187. Since the resulting value is positive, we have to replace the limit that has the same sign when plugged into the function. But again, let's check the relative error of the defined roots. Epsilon is the absolute value of 0.438 minus the previous value, which is 0.625, all over 0.438, and that is equals to 0.4286 or 0.429. still far from the stopping criterion. For our fourth iteration, the lower limit will remain 0.25, while instead of 0.625, the upper limit will become 0.438. Well, I suppose that you now understand how to determine the roots of an equation using bisection method. Let me now show you my MS Excel computation that presents the convergence of this problem. As you see, it will take 13 iterations to satisfy the stopping criterion. And as you also notice, the value of the roots is equal to 0.36. Since this is the graph of the equation, obviously it has two roots. Well, the best way to test if you learn something is to redo what you see. For your practice, try to prove that the other value of the root is 1.89. So that concludes the discussion of manual computation using bisection method. This last part of the video is dedicated for the computerized computation using bisection method. I will focus the discussion not on the MS Excel itself, but rather on the program language embedded to it, the so-called VBA or the Visual Basic Application. So, if this is your first time to use VBA, you have to first activate its tab. Open your MS Excel, then click the File tab, then go to the Options, then under the Customize ribbon, normally Developer tab is disabled. So check the box of the developer, then click OK. A new tab should appear on MS Excel, normally besides the View tab. Then, go to the Developer tab and click Visual Basic. A new interface should appear. To start writing a code, we will insert a module that will contain our algorithm. So click Insert and Module. We will start the code by sub-procedure. It will be enclosed by sub and end sub statements, which will contain the instruction that will feed to the computer. The bisection text is the general name of this instruction. It means I can call this instruction later using another module or another sub procedure. If that sounds techy to you, say for example that I want to determine the summation of these numbers. I can add them manually. 1 plus 2 plus 3 plus 4, or I can use the summation function of the Excel. That's what I'm trying to say earlier, to call the instruction by its name. Now that you are familiar with the sub-procedure, let's create the instruction inside it. Let's first define the variables and their values to be used by the algorithm. So we have the lower limit, the upper limit, the stopping criterion, the relative error, present refined value of the limit, defined value of the limit, and the number of iterations. Now we will implement procedure 1 to make sure that the initial guesses contains the root. In this instruction, we will use if-then-else statement, where if the condition is met, the included instruction will activate, otherwise it will be ignored. This is the condition of the code. You can change that with any statement that suits your computation. On the other hand, this is the instruction to be carried when the statement is satisfied. You can also change that part. In this particular line, it will end the code if the multiple of this function is positive. In other words, they have the same numerical sign in line with procedure number 1 of the bisection method. The procedure number 1 text is made possible without prompting an error since we place apostrophe in the very start of the line. That signifies that anything behind the apostrophe is just a comment. For the iterative solution, we will use do until loop since it is a loop command that will never stop until the criteria is met. In this particular line, it will end the loop or the iteration if the relative error becomes smaller as compared to the stopping criterion. Both procedure 2 and 3 should be included within this loop since they are the iterative part of the bisection method. For the implementation of procedure number 2, we will simply use a mathematical expression that take the average of the limits, and also we are counting the number of iteration. While for the implementation of procedure number 3, again we will use if-then-else statement, but this time with the else-if part. Well, it's just a longer version of the one we used before with the same idea. Again, the idea is in line with the procedure 3 of the bisection method. Well, this one is for relative error with a simple mathematical expression. So that concludes the content of the do until function. And once the do until loop is done, it means that the solution has reached the convergence. Well, these remaining lines of the code will just copy the contents of the variable from the BBA and paste it to designated Excel coordinates. The first number signifies the number of row, while the other is for column. To test the code line by line if there is a bug, you may press F8. As you notice, each variable is updating. Well, if you want to run the code immediately, just press F4. As you see, the output of the code is presented in the Excel sheet. It means that it took 13 iterations to extract the root, which is equals to 0.361, with a relative error of 0.00051. You can update the initial guesses to determine the other value of the roots if you want to. Another important note is to make sure that you save as the Excel file as Excel macro enabled workbook, because if not, the written code will be discarded. Or in other words, it will be deleted. So that's it for this video. Hopefully you learned something. Thank you for watching and see you soon. Keep safe, guys.